Greetings, everybody. Learning is a hobby. I wanted to do the second video for Appendix 2 in Spivak for Chapter 4. I want to finish up the exercises for that so I can move on to Appendix 3, which hopefully I'll get at least one video out for that today. It is kind of a long section, and I haven't started even reading the section yet. And then, there's actually like 10 problems, I think, in the exercise set for it. So we'll see how much I can get done for that today. But anyway, I want to finish up the exercises for Appendix 2 right now, and which should be a quick video because there's only 3 questions and they're all very similar. So this video is probably going to be like 5 minutes long. But anyway, and before I start, let me just apologize for my voice. It is allergy seasons, and unfortunately, I do suffer pretty bad from seasonal allergies, which is why my head is all stuffed and my eyes are red and itchy, and hopefully I don't go into a sneezing fit while while I'm recording this video, because then I'm gonna have to go back and record it all over again. But those are my problems, not yours. So let's see if we can get through the exercise set here before that happens. Okay. So, like I said in the last video, there's actually only 3 exercises for this section. And they're relatively straightforward and kind of short, so it shouldn't take us too long to go through them. But let me start by reading out problem number 1. Consider a cylinder with a generator perpendicular to the horizontal plane. The only requirement for a point XYZ to lie in the cylinder is that XY lies on a circle, X squared plus Y squared equals C squared. And he wants us to show that the intersection of a plane with this cylinder can be described by an equation of the form in parentheses alpha X plus beta squared plus Y squared equals C squared. And he wants us to say what possibilities there are. So here, just drawing the picture, this is very similar to the example that he did in the chapter in the appendix itself, when he was showing that the intersection of a plane with a cone gives you a conic section. So using the same construction for coordinates that he has in that example in the appendix, we have that the points on the points XY on the plane have this form here: alpha X plus beta comma Y. And you just plug that into the constraint curve for the cone, and you get what you want. So, and then when you multiply it out, you get this expression here, and we can use this to analyze the type of curves that you get. So if P is parallel to the XY plane, then you can choose your coordinate system on the plane then to be, let me just go up real quick. Actually, let me draw, do I have my marker here? What did I do with it? If the plane is horizontal, let me see if I can actually draw that in the picture here, because I didn't make a picture representing that. The plane, the intersecting curve would look like this, and you can choose, let's call this point Q here. You can choose that point to be your point Q, and then your coordinate system, the X value would be the same as the X value down here. And remember, what the Y coordinate points out of the screen, so the Y coordinate would be the same as well. So you just get the equation X squared plus Y squared equals C squared from that. In other words, alpha is 1 and beta is 0. So that obviously gives you a circle, which should be intuitively clear that that's what you get when you intersect the cylinder with the plane. Then case number 2, if the plane is vertical, then the X coordinate will be constant, right? So I'm just giving the constant name. I'm calling it X hat. Then again, going back up to the equation that we derived, that means that Y squared is C squared minus, in parentheses, alpha X hat plus beta squared. That's a constant, so you get two vertical lines. One either two vertical lines, or one vertical line, or the empty set. Again, this should be clear, just by thinking about it. If you intersect the cylinder with a vertical plane, obviously you're gonna, if you cut it, non-tangentially, I guess, right, you'll get 2 straight lines. If you cut it with a plane that's tangent to the cylinder, you get 1 straight line. Or if the cylinder doesn't intersect at all, obviously you get the empty set. That's case number 2. Case number 3, if the plane is neither vertical or horizontal, then this equation is the equation of an ellipse, so you get an ellipse. So those are the 3 cases. Okay. Question number 2, there's a couple parts to this one. In the figure, which I have drawn below terribly, but bear with my terrible drawing ability. Hopefully you can make out what this picture is saying. In the figure, the sphere S1 has the same diameter as the cylinder, so that its equator C1 lies along the cylinder. It is also tangent to the plane P at the point F1. Similarly, the equator C2 of S2 lies along the cylinder, and S2 is tangent to the plane P at F2. So hopefully, again, from the picture, you can see what that's saying. L is the vertical line from C1 down to the point. Let me label this so it's easier to see what Z is. This point here is Z. So this point lies on the plane as well as on the cylinder. So in other words, it's part of the intersecting curve, right? So this line segment here is what he's calling L, and the distance from Z to the point of tangency on this sphere is F1. Okay, and then same thing for F2 and C2. Hopefully, like I said, I'm sorry for my terrible drawing, but hopefully you can at least parse what I'm trying to say there. All right, there's 2 parts to this. Part A says, let Z be any point on the intersection of P and the cylinder. Explain why the length of the line from Z to F1 is equal to the length of the vertical line L from Z to C1. Let's do that first, and then we'll take a look at part B after. All right, so here just bringing out a portion of the picture, just blowing it up so it's easier to see what's going on here. So here we have the sphere, the equator. Let me draw that in here. The equator is this curve here, right? So L is this length here, which I'm calling A, just for when easier just to see what's going on here when I show you the derivation. And then this length here I'm calling B, which is the line segment from Z to F1, which is the other point of tangency. So if you look at the picture here, both of these lines are tangent to the sphere, which means that the line segment L here and the line segment which is the line segment from Z to F1, notice that they have, because they're tangent to the sphere, they have to make right angles with the radii of that sphere. And since these 2 sides here are the radius of the circle, that means that if we draw a line from the center to Z, which is this blue line that I have drawn here, we have 2 right triangles where 2 of the sides are congruent, right? This side is congruent to this side, and obviously they share the hypotenuse, so that side obviously is congruent in both of the triangles. And if I call the angle here alpha, the angle here beta, the angle here theta, and the angle here phi, then we get that L, I'm calling just the way I'm defining things here, I'm calling the blue line segment L. So let L be the line segment connecting Z to the center of the sphere. Then L sine alpha is equal to the radius, right? That's just by trigonometry, which is the same length as L sine beta, which implies that sine alpha equals sine beta, which implies that alpha is equal to beta, since alpha and beta are complementary angles, right? So they have to be acute. This implies also that theta equals phi, which means that the triangles are congruent, which means that the length A has to be equal to the length B, and that's the proof. All right. So that's the answer for part A. Let's take a look at what they want us to do for part B. Part B says, by proving a similar fact for the length of the line from Z to F2, show that the distance from Z to F1 plus the distance from Z to F2 is a constant, so that the intersection is an ellipse with foci F1 and F2. The fact the fact that the distance from Z to F2 is equal to the distance from C2 to Z is the same exact proof as for part A, so I didn't redo that, but hopefully that's clear. So all we have to do is show that the distance from ZF1, the distance ZF1 plus ZF2 is the same, is constant for any value of Z that lies on the intersecting curve. So if you call L1 the line segment from C1 to Z and L2 the line segment from C2 to Z, and let script L, I had to give these names, so let script L equal the distance from C1 to C2, then the distance of Z to F1 plus the distance of Z to F2 will always equal L1 plus L2, because those L1 is congruent, is equal to ZF1, and so on and so on. So since that sum is always constant, no matter what the point Z is on the curve of intersection, then by definition that gives you an ellipse, so with the foci F1 and F2, and that's it. That's the proof. Okay, so that's question 2. Question 3 is very similar, so I kind of gave this one a little short shrift just because it's almost the same type of proof as in part 2. So let me just read out the question though. Similarly, we use figure 1 below to prove geometrically that the intersection of a plane and a cone is an ellipse when the plane intersects just one half of the cone. And similarly, use figure 2 below to prove that the intersection is an hyperbola when the plane intersects both halves of the cone. So here again, you could see my terribly drawn pictures here, but again, hopefully you can get a sense of what the geometry is. The proof for figure 1 is exactly the same as the proof for for question 2, with the exception that the distance C1 plus C2 is actually the distance has to be taken along the generating curve of the cone, as opposed to the vertical line from C1 to C2. So it's basically the same proof. For C2, it's also the same proof, but it's a little more complicated because the plane is vertical, so you have two halves of the cone. But again, if you take the lengths to be along the generating curves for the cones, then you could see that ZC2 minus ZC1 is always constant, and that's equal to ZF2 minus ZF1 by same geometry from question 2. Therefore, the curve is a hyperbola, right? Because you get the conditions for a hyperbola that has foci F2 and F1, and that's it. That's basically the 3 questions from section. From chapter 4, appendix 2. So I haven't even read appendix 3 yet, so I have to actually run and do some chores real quick. But when I'm done with that, I'm going to come back and read appendix 3. Maybe I'll be able to write up the notes for that and make the video for that today. But it's going to take me obviously a little while to do the problems, because I haven't even read the section, let alone even done any of the problems there. So maybe I'll be able to post that video tomorrow or the day after or something. So, but definitely today I think I'll be able to post the video for the appendix 3 summary. So again, thanks for watching, guys. Like and subscribe if you enjoy this content, so that YouTube knows to share it with other like-minded people. It helps the channel grow and get, like I said, get the content out to people that enjoy the same things that you and I do. So until my next video, which hopefully will be today, keep learning, everybody, and I'll see you in the next one.